Hey folks, we're going to dive into some torque problems right now. So we have a bar here. Multiple forces act on a bar that is attached to an axle as shown. Determine the net torque on the bar. So there's the axle. I've included some distance measurements between the axle and the forces, and then an angle where appropriate. This 3 Newton force should be at a right angle to the bar itself. So I'm calculating net torque, and I want to decide like whether my torques are positive, negative, or zero. This first torque is going to be positive because it would cause counterclockwise rotation. This second torque, however, is going to be negative because it would cause clockwise rotation. And then this third torque is going to be positive because it would cause counterclockwise rotation. So these two forces, the 5 Newton and the 2 Newton, they are actually in the same direction, whereas the 3 Newton force is in the opposite direction. So to write that out, my net torque is going to be the torque due to the 5 Newton force plus the torque due to the 2 Newton force minus the torque due to the 3 Newton force. And so I'm going to use torque equals RF sine theta for each torque. Okay, so net torque. The torque due to the 5 Newton force. The value of R from that axle is 0.2 meters. The value of the force is 5 newtons. And we're going to use the sine of 70 degrees for that. All right, so that's pretty simple for that one. The 2 Newton force over here, this one's a little bit more complicated. The distance from the axle is these two distances combined, so 0.8 meters, times the magnitude of the force, which is 2 newtons, times the sine of 100. So that takes care of that one. Minus, and this one I'm going to make really simple. This is the 3 Newton force. Its distance from the axle is 0.4 meters. The magnitude of the force is 3 newtons, and I'm just going to stop there. I'm not going to do sine theta because that angle is 90 degrees. The sine of 90 degrees is equal to 1. So anytime I see a right angle, I know I can skip the sine theta part. If I throw that in my calculator, I get a positive number, a positive 1.3 Newton meters. So that takes care of that one. It's just a straight calculation. Okay, this next one is as conceptual as it is a calculation. Multiple forces act on a bar that can rotate at one end as shown. The forces are equally spaced out. Rank the torques due to each force from highest to lowest, noting any ties. And so it doesn't give me any distance measurements, and it's asking me to rank these torques. Now, I know that torque is R parallel to F, and I know I also don't have these measurements. So I'm not going to include the sine theta. All of these are at a right angle to the bar. And instead of using measurements that are given, I'm going to make up my own because I'm just ranking them. If they are equally spaced, then we're going to put this first torque at a distance of 0, and then 1, and then 2, and then 3. So I can quickly calculate the torques as if I knew the distance, as if it were a 3-meter long bar, and that's it. So the torque due to force A, that's going to be 0 because that's at the axis. The torque due to B, that's R times F, is going to be 1 times 4 newtons. The torque due to C, well, that's 2, a distance of 2, twice the distance, times 3 newtons, which is a torque of 6. And then the torque due to force D, well, that's 1, 2, 3 spaces away, and that's a force of 2. And so that's a magnitude of 6 for torque. All right, so that gives me my ranking right there. So I didn't get distances, but I knew the relative spacings, and I just take into account that they're 0, 1, 2, and 3 spaces away. So my final ranking is the torque due to C and the torque due to D are the greatest and equal, they are greater than the torque due to B, and that is greater than the torque due to A, which is 0. So the position of the axis matters a lot there. Okay, last one. Forces act on a ball as shown. Write an expression for the net torque on the ball. The force mg acts on the center of the ball, while Fn and Ff both act on the lowest point. We'll talk a lot more about this when we get into the forces, like Newton's second law, and even like energy and momentum. But when you draw a free body diagram for a big object, you draw the forces where they act. So as it says, the force of gravity acts at the center of gravity, which is the center of the ball. The normal force and the friction forces are caused by the floor, so their arrows start at the bottom of the ball. And so my net force, my net torque rather, is going to be very simple. If I look at the forces, I can see that the force of gravity originates at the center. That's an R of 0. I can see that the normal force passes through the center. That's an R of 0, or it's an effective R of 0. And so really the net torque is going to be the torque due to the force of friction. So the net torque is going to be the value of the radius of the ball times the magnitude of the force of friction. And that's actually going to be it for that, because there's no torque from gravity or the normal force in that situation. And that's it.